Uh, so today's speaker is Sengupta from SUNY at Binghamton or Bingham University SUNY, and he speaks on nilpotent sequences. So please.
Thank you. So my work is about studying iteration of integer polynomials and how it behaves modulo primes and how, for which situations you will get 0 in the orbit of such polynomials when you start with a given integer. So I'm defining a polynomial sequence to be any integer sequence Rn, which has a generic polynomial u. And by that, what I mean is that u0, well, this notation is for the nth iteration of u with itself. So u compose u with itself, it's going on like n times. And what I want is u of R0 to be equals to R1, u of R1 to be equals to R2, and so on. So this is the nth iteration of u at R0, and that is supposed to be equals to Rn for each positive integer n. If there is some positive integer n for which Rn is exactly equals to 0, then we will say that this polynomial sequence is a nilpotent sequence. And if for infinitely many positive integers n, Rn is equals to 0, we will say that Rn is infinitely nilpotent sequence. So this is the definition about the sequences. And then we can have similar definition, one extra, I guess, for polynomials. So say you are given a number R and you are given a polynomial U. We will call calligraphic O sub U R to be the set of all iterations of U at R. So basically it forms a sequence. If you add R at the beginning, then it would be exactly this sequence, Rn. We are going to call U locally nilpotent at R if for each prime P, there is some iteration MP. I'm writing M sub P because MP will almost always depend on P in such a way that P will divide this iteration at R. So this is what the locally nilpotent means at R. And nilpotent is similarly defined. When I said similarly, I mean you are actually going to see 0 in this orbit. And if it happens at least once, then we will say that U is nilpotent at R. And if it happens infinitely many times, we will say that U is infinitely nilpotent at R. And the first n for which we will see the 0 for either case really, that will be the index of U at R, or sometimes nilpotency index of U at R. So this index is only defined when U is nilpotent, basically. And we are going to maintain the idea that index is a positive integer. We are not going to consider 0 as a possibility for index. And there's some notation that we would like to use throughout the talk, starting with this one, NRMD. So R basically means your starting point, R, as mentioned here. M means the index, and D means the degree of the polynomial. So if you take the union over all the D's, all the degrees D, I guess you can take D to be greater than or equals to 1 instead of D greater than or equals to 0, because the constants doesn't really give us anything. The non-zero constants, I mean, it's going to stay the same. So if you read 0 or if you read locally nilpotent, you're at max, you're going to have finitely many divisors. So it doesn't make sense. So basically D greater than or equals D equals to 0 is a empty set, so to speak. So when you take the union over all the D's, we are going to denote that set by Rm. And R is going to be all of these things where D is greater than or equals to 1 and M is greater than or equals to 1. So in other words, NR is going to denote the set of all nilpotent polynomials at R. So some examples. If you have any R, then for each non-zero polynomial Q over Z, this is going to be nilpotent because you can just plug in R and the value is going to be equal to 0. So this is nilpotent at R of index 1 and degree, well, degree of Q plus 1. And for non-trivial examples, so I guess you can call index 1 polynomials as trivial examples because it's always going to be a multiple of x minus R if you're starting from R. You can consider this one, minus x cubed plus 9x squared minus 25x plus 25. So if u is defined this way and you start from 2, then one can check that 2 will go to 3, 3 will go to 4, 4 will go to 5, and then 5 will go to 0. So basically at the fourth step, we are getting 0. That means u is nilpotent at 2 of index 4, and this is of degree 3, which is obvious. Similar checking can be done on this polynomial, but in this case, you can start from 3. So 3 will be taken to 2, 2 will be taken to 1, and 1 is going to go to 0. So in this case, u is nilpotent at 3 of index 3 and degree 3. One example might be interesting, which is non-nilpotent. So we can consider x squared minus 4x. And u3 is minus 3, and u of minus 3 is 21. And after that, one can check very easily that this is going to be strictly greater than 0 for every x which is larger than 5, strictly larger than 5. So that means if you start at 3, you will never reach 0. So u is not nilpotent at 3. And finally, this example is interesting because this is telling us that, well, okay, maybe I can go back here. So one thing is clear, that if u is nilpotent, then it is locally nilpotent because you are having 0 in the orbit. So for every prime, you can consider whatever that index is to be our NP. So that is pretty clear. But what about the other one? Can there be polynomials which are locally nilpotent, but not nilpotent when a starting point is given? Well, yes, that is true, which is exhibited by this example. You can consider ux to be equals to x plus 1. Then by induction, it's clear that the nth iteration of u at 1 is going to be n plus 1. So you will never see 0 in the orbit. But for every prime p, one can see that the p minus 1th iteration of u at 1 is p, which is congruent to 0 mod p. So for every prime p, although the MP is not our choice, but if nothing else exists, then we can take MP to be equal to p minus 1. But anyway, according to our definition, MP is not something that we are choosing. But in any case, we can guarantee that this is locally nilpotent, but not nilpotent. So there exist polynomials which are like that. It will be 0 mod p for every prime p, but it is not actually close to 0, the number 0. And in fact, this is not something unusual that happens with 1. It happens for each and every integer that we see. But for 1, there is a very nice case. So what is known here? What is published so far? So for 1, we have a complete classification of all the polynomials that are locally nilpotent at 1. So here's how it goes. If you start with a polynomial which is locally nilpotent at 1, then either 1 will be taken to 0, which is this one, this family of polynomials, or 1 will be taken to 2. And now where 2 goes, that is a question. So 2 either has to go to 0, or 2 has to go to 3. Now, if 2 goes to 0, then this is the family that we are looking for. And if 2 doesn't go to 0, then it must go to 3. Now, from 3, we start this thing again. 3 either has to go to 0 or 3 has to go to 4. If 3 goes to 0, then this is the family of polynomials for which this happens. And if the 3 doesn't go to 0, then it has to go to 4. But from here, you won't ever get 0. It will continue like that. 3 has to 3 has to go to 4, 4 has to go to 5, 5 has to go to 6, and so on. So, and that can be shown by induction. And using the idea that we can always pick a prime P such that we can trap it. We can have like something repeating indefinitely. So we will never see 0 modulo P. And since it's an induction thing, on the only polynomial that it will satisfy is going to be x plus 1. So if you start from 1, there is exactly one polynomial which is going to be locally nilpotent, but not nilpotent. And one can also see that if you start from 1, then the maximum index is 3. We also have a complete classification of polynomials. Local nilpotent polynomials at -1. So there is actually a relation between -r and r, which we will describe below. But theorem 2.2 is more like a correlate with theorem 2.1 because we can always switch between r and -r. I will show that later. And exactly the same thing happens with the switching formula that I will tell you. And in here also, the locally nilpotent, but not nilpotent, there is only one of them. And the maximum index is also going to be 3. So 2 more than the r that we started with. We also have a complete classification of locally nilpotent polynomials at 0. So in this case, you see there's two infinite family of locally nilpotent polynomial, which is not nilpotent, unlike 1 and -1. So 1 and -1, we will see 1 and -1 is are the only integers for which there's a unique polynomial so that it is locally nilpotent but not nilpotent. For all the other integers, you will get infinitely many polynomials which are locally nilpotent but not nilpotent. An interesting thing about 0 is that you have two families here, which was also, well, I guess in here it was exactly one polynomial. So in here there are two families, not just one polynomial, but two polynomials and also two families. And you will have index maximum equals to 2. So here also you see the +2 thing. If you're starting with 1 or -1, then the maximum index is 3. If you're starting from 0, then the maximum index is 2, which is 2 more than 0. And we also have complete classification of all polynomials which are locally nilpotent at R, but not nilpotent at R. We had to stop at certain point because the locally nilpotent polynomials, turns out it was extremely hard to understand because ultimately we are looking at polynomial iterations, and these are not very well understood in terms of actually classifying things. We have a lot of density results. We have a lot of results which is connected to the dynamical model length conjecture, but not exactly in this format. But what was working in our favor
Excuse me.
Yes.
Is we in this context just you, or is this a team effort?
No, it was me, and some of the suggestions was by my advisor, Professor Borisov from SUNY.
Okay.
Yeah, but the proof are like if in here the proofs are entirely mine.
Okay.
But I've included here one or two things where the proof and the statement are both from my advisor. So I've stated that precisely.
Okay.
Right. So what was working in our favor, if we want to consider only locally nilpotent polynomials, but non-nilpotent ones, is that these polynomials, if they exist, then they are going to be they cannot be of degree greater than or equals to 2. In equivalently, if we have a polynomial of degree at least 2, and we look at the odd bits, modular primes, then there's going to be a positive density of primes for which you will never see 0. And that is an outcome of a paper written by 5 or 6 people, I think. And 2 of the people that I know personally is Professor Scanlon from Berkeley and Professor Tucker from Rochester. And that is why I only had to consider only linear ones. And linear ones, we have some easy iteration formula. And that is what was working in our favor. And we were able to capture all the families of polynomials for which it is locally nilpotent at R, but not nilpotent at R, using this fact that if it exists, then it has to be linear. So this is what we know so far. And what was done last year is this. In the previous list, we talked about plus or minus 1 and 0. This list talks about 2 when R is equal to 2. And this gives us all the polynomials which are nilpotent at 2, because we are done with local nilpotent things. So this is the thing that we did not understand or could not understand how to do last time. So that is what we are focusing on, just to find the nilpotent ones. So this is a picture of 2. So there's 6 possibilities or 6 families. And if we try to understand them in terms of sequences, sequences in the sense that how are the numbers like going from where to where exactly, because this can be understood, this can be read as polynomial sequences, because it is associated to a generating polynomial, which is ux here. So there are exactly 6 possibilities. If your polynomial sequence is a nilpotent sequence and you start at 2, then either you have to go directly to 0, for example, using the polynomial x minus 2, or you can travel to 1 and then travel to 0, which you can use for which you can use x minus 1, or you can travel from 2 to 4 and then from 4 to 0, or 2 to 3 and then 3 to 0, 2 to 4, 4 to 6, 6 to 0, and finally 2 to 3, 3 to 4, 4 to 5, and 5 to 0. There is no other way of traveling from 2 to 0 if using a polynomial sequence. One thing should be made clear at this point, that this is really a question about integers. Because if you have any collection of finitely many numbers, well, when I say numbers, I mean integers or rational numbers, whatever, doesn't matter. We always have this Lagrange's interpolation method. So we can always find polynomial which will hit exactly these numbers in the right way we want. But this polynomial, there is no guarantee that the interpolation polynomial is a polynomial over Z. By using that idea that we are restricting this polynomial to be Z, we were able to filter out the unwanted ones. So these are the only ways that it can happen. These are the only ways that the interpolation polynomial is going to lie over the set of integers, over the ring of integers. So this is 2. Here also one can see that we have started from 2 and the maximum index is 4. So here also you have the plus 2 thing. But this is where it stops. So for 0, the maximum is 2. for 1 and minus 1, the maximum is 3, sorry. For plus and minus 2, the maximum is 4. And that's where this r plus 2 thing stops. From starting from 3, the maximum index is always going to be equals to r. So if r is greater than or equals to 3, then all the sets are n r, comma r plus 1, r comma r plus 2, and all of the sets are going to be empty. So this is the case of 3. And you can see that the maximum index is 3 here. And that is the maximum that you will get. But there's something else going on with 3, which we will not see in 4. And that is index traveling from 3 to 0 with index 3. So there are 4 ways of doing that. 3 to 2, 2 to 1, 1 to 0. 3 to 4, 4 to 2, 2 to 0. 3 to 4, 4 to 5, 5 to 0. And 3 to 2, 2 to 4, and 4 to 0. There are 4 ways of doing that. But if r is greater than 3, strictly greater than 3, then there is exactly one way. First of all, the maximum index is 4. And there's exactly one way that you can travel from r to 0 with index r. Okay. And you can see this is the only one of index 4. And there is something interesting also going on here. After index 2, you will see 4 right away. There is no index 3 when you start with 4. And that is one of the conjecture, which I will state at the end, that if your R is large enough, I was not able to determine how large R is supposed to be. I believe that 4 should be enough, but I have no proof. The assertion is this, or the question is this, rather. I shouldn't even say it's a conjecture. It is more likely to be a question. If R is large enough, then is it true that if U is a polynomial of index m being larger than R over 2, or I guess if R is odd than R plus 1 over 2, then the next one is going to be index R. There is nothing in the middle. From R over 2 to R. That's how it's going to look like. So this is the question, is this true? I have no proof of that, but it seems like it is, well, it is definitely true for R equals 4. It's definitely true for R equals 5. I have not checked 6, but I believe it will be true, but anyway, again, I have the proof of that. So as I mentioned in the last one, if R is greater than 3, actually greater than or equals to it should be equals to 3, then M is less or equals to R. So in other words, in R4, in R5, and R6, all of those things, when R is equals to 3, it's going to be an empty set. Maybe I should not say 3, 4. I should say NR, R plus 1, NR, R plus 2, NR, R plus 3. All of these things are going to be an empty set if R is at least 3. And we would like to know what the maximum index polynomials look like. It turns out that if R is strictly greater than 3, then this is the only one. And one can check that this polynomial is the one that takes R to R minus 1, R minus 1 to R minus 2, and so on, 1 to 0. Now we can talk about the correspondence that I stated earlier. So if we have information about local nilpotent or infinitely nilpotent polynomials at R, then we will know about locally nilpotent, respectively nilpotent and infinitely nilpotent polynomials at minus R. Of course, it makes no difference if R is equal to 0. So we can say R is not equal to 0 in this case. And this would be the idea. If U is nilpotent or any of these things really, then we can define a V in this fashion. v of x is equals to minus of u of minus x. And then using induction, it's easy to show that the nth iteration of v at minus r is minus of the nth iteration of u at r. So if this thing is 0, then so is this at minus r. And if this thing is divisible by p for some p, then of course this is going to be the same. So it is enough to treat the non-negative r's. And enough in the sense that we just by the information that we have collected for nilpotent polynomials or the other ones at non-negative r's, we should be able to just change it this way. Change the u to v in this fashion to get the nilpotent or the other ones at minus r. So this is what we can say about the maximum index, that if r is equals to 0, then the maximum index is 2. If absolute value of r is equals to 1, then the maximum index is 3. If absolute value of r is equals to 2, then the maximum is 4. And if r is strictly greater than 2, then the maximum index is absolute value of r. Okay, so now we talk about the infinitely nilpotent ones, specifically infinitely nilpotent ones. Suppose that Rn is a polynomial sequence. So that means it comes with a generating polynomial u. Then the following are equivalent. So R is an infinitely nilpotent sequence if there exists some positive integer m, such that either you have 2 consecutive zeros, or you will just go back and forth between 0 alternatively. Well, why is that? One direction is obvious, b to a, because if you see 0 at Rm, both Rm and Rm plus 1, then using the idea that it comes with a generating polynomial, you will see 0 infinitely many times, and the same logic goes here. So b to a is clear. A to b, for a to b, what we used is the idea that if Rn is infinitely nilpotent sequence, then the generating polynomial is nilpotent at 0. And if we go back, then we can see we have a very good idea about how zeros actually look like. So we just ignore 1 and 2 because those were local nilpotent ones, not nilpotent ones. These are the 2 nilpotent ones. So either you are going to go 0, 0, 0, and so on, or 0 goes to 0, 0 goes to 0, and so on, or you just go from 0 to some non-zero integer a, and then a will be taken to 0, and then 0 goes to a, and a goes to 0, and so on. So it will be, so that's precisely what was working in our case when we were trying to show that A implies B. So in other words, if we write it out, then we are really saying that if Rn is an infinitely nilpotent sequence, then it must be of the form this. After a certain point, we are going to see 0 like this. It's going to become stationary at 0, or it is going to switch between 0 and Rn plus 1, Rn plus 1 to 0, and then 0 to Rn plus 1, and so on. So if we can classify the sequences, which looks like either 3.1 or 3.2, then we should be able to classify all infinitely nilpotent sequences. Well, for the first one, it's easy because we are eventually seeing 0, so we know how this is supposed to look like. It's if the generating polynomial u is supposed to look like x times px, or for some non-zero polynomial px, and I have used that in order to narrow down the possibilities. And these are the possibilities. Either m is 0, in which case it is just a 0 sequence, so we are starting from 0 and we are sticking with that. Or m is equals to 1, So there is an R0, which can be arbitrary. I guess if I am careful about this, then I should say arbitrary, but not equals to 0. Otherwise, m equals 1 and m equals 0 are the same thing. So I should add that R0 is not equals to 0. And then m equals 2. In that case, one has to be a bit more careful because not everything will go there. R0 definitely has to divide 2. So all the possibilities of R0 is it lies between plus and minus 1, plus and minus 2. And R1 has to be 2R0. So the number of these sequences when m is equal to 2 is finitely many. Now this classifies the infinitely nilpotent sequences, which are of the form 3.1. So it becomes stationary at 0. What would be the idea for the sequences that looks like 3.2? So it flips between some 0 and some non-zero number. Okay, here's the idea. If Rn is a sequence and U is a generating polynomial of that, then all the subsequences of the form Rmn, they're also going to have a generating polynomial. And that polynomial, one can take it to be the mth iteration of U. It's going to take exactly those values. So we can easily check that this will also be a polynomial sequence. So if Rn is a polynomial sequence, then Rkn, for example, where of course n still starts from 0, is also a polynomial sequence. So if we know what this looks like, or the classification of this, then instead of looking at U, we can start looking at the second iteration of U with itself, and then we should be able to trap it. 0 will go to 0, 0 will go to 0, and so on, provided that m is even. If m is odd, then we start from n equals 1. So from this spot, and then we should be able to trap it like this. So that was the basic idea in classifying the polynomials that looks like the infinitely nilpotent sequences that looks like 3.2. And right away, looking at this classification, one can see that it cannot be more than 5. Actually, yeah, more than 5. Yes, that's right. More than 5 in this situation. So that I had to check by hand that it's m equals 4 and m equals 5 were also not a possibility. But the idea is basically that instead of looking at U, you had to check the second iteration of U in order to trap these zeros. And basically, it's a more or less a corollary, or I guess a podism of 3.8. Okay, now here is something which is a byproduct of these things. What if instead of looking at 0, we have a bounded integer sequences, a bounded integer sequence. So it's a polynomial sequence which is bounded. Well, it's an integer sequence. So there's going to be some integer which will repeat infinitely many times, say s. Then I can define a new sequence, Sn, S sub n, by letting Sn equals to Rn minus s. Then I have transformed this Rn sequence into a new sequence, which is Sn, which is an infinitely nilpotent sequence. And that will also have a generating polynomial, which is basically this, Vx equals to that. And it's easy to check that the induction also works very nicely. So we can also classify all bounded polynomial sequences using this theorem 3.8 and 3.9. Now, what exactly were used to get these results? Well, first of all, excuse me. First of all, let me give you an idea on how I proved that Well, actually, it is not my proof. I think it was a Putnam problem, but it was not a recent problem. I can't remember which year, but it was definitely a Putnam problem. So I used most of the proof here. But there was another situation of local nilpotent polynomials. For that, that part of the proof was mine. This is definitely a Putnam problem. So what was the idea here? You start with U, a nilpotent polynomial of index m for some positive integer m. If U is equals to 0, then we say right away that m is equals to 1, and we are done. It has to look like xpx for some non-zero polynomial px. Otherwise, you define this u sub i's in this way. So u sub 0 is going to be just a u at 0, and u sub n is going to be these differences. The n plus 1th iteration of u at 0 minus the nth iteration of u at 0. And using the idea that these are actually polynomials, which takes polynomial values, we know that if n and m are two different integers, then the difference n minus m is always going to define always going to divide fm minus fn. So that is always true. So using that, I can say that un is it always divides un plus 1. One can also check that your um is equals to u0, which is u of 0, because by hypothesis, this is nilpotent at nilpotent of index m. So what we have shown until now is this. We have this chain of divisibility relations. U0 divides U1, U1 divides U2, and so on. Um minus 1 divides and is actually equals to the starting one. So that basically means that un is exactly either plus u0 or minus u0. The magnitude has to be the same for each n. Also, if you add up all the ui's up to m minus 1, then this looks like a telescopic series. And you will end up with um0, which is just 0. So we know that up to this one, actually it is true for every n, but in particular up to this one, m minus 1, it's all of these guys are plus or minus u0. And if you add them up, you're going to get 0. So there's exactly half of these things which are u0, and the other half is minus u0. And since we are taking m to be greater than 1, this number is not equals to 0. So plus or minus u0 is not equals to 0. So we should be able to find some k between 1 and m minus 1 such that we have this situation. uk minus 1 is positive, uk is negative, or the other way. In any case, uk minus 1 is equals to minus of uk. So if we write this out using this thing here, then that will imply that the k plus 1th iteration of u at 0 is the k minus 1th iteration of u at 0. So you have this 2-period thing that shows up here. Thus, un plus 2 is at 0 is going to be un at 0 for each n which is larger than or equals to k minus 1. And in particular, since m minus 1 is greater than or equals to m is greater than or equals to k, so m should also satisfy this. That means um of 0, which is equals to 0, and that is equals to m plus 1, m plus 2, 0, which is equals to u2 of 0, and that means m must be equals to 2. So if you start from 0, the index has to be 1 or 2. All the other ones, union 03, 04, 05, and so on, those are really empty sets. Other thing that we used was this idea that this is an observation by Professor Borisov. What he observed was this, that if you have some nilpotent polynomial u, we understand the case r equals 1, so I'm just ignoring that. And also I'm taking R to be positive because the -1 can be understood similarly. If you have some K for which you have a sequence of equalities up to UR plus K minus 1 equals R plus K, and then one inequality, which is this, then it cannot, so K is actually bounded. So this chain of equalities that you see, which is increasing by 1, is R goes to the next one, R plus 1 goes to the next one, and so on. This cannot go on indefinitely. This has to stop. And compared to R, this K is quite small. K is actually less or equals to CR, where CR is basically the set of all integers, positive integers, such that, well, maximum of the set, such that R is greater than or equals to S factorial minus S minus 1. This was the basis of the proof of all of the arguments that I stated as new results. So in all of those cases, what I did was I divided it up into cases. So I tried to see what is the maximum value of K that is possible. And then case 1 is K equals 0, case 2 is K equals 1, and so on, up to K equals something which is quite small relative to R. And how would one prove that? Something like this. This S factorial comes quite naturally, actually. If you have this sequence of equalities, then if you consider this polynomial ux minus x minus 1, then this has all of these zeros. So we know sort of how it looks like. It must look like x plus 1 plus all of these things times some non-zero polynomial gx. Well, yeah, because because of this. Because of this, gx has to be non-zero. And what is u of R plus K? That's that. And okay. So what is the difference? What is the K plus 1th iteration difference of u with the Kth iteration difference? Well, which we are denoting by UK, by the way, like we did in here. So this is really equals to that. After we cancel things out, some things are going to be canceled. And then if you write it out, it ultimately boils down to 1 plus K factorial times G of R plus K. And the minimum value of this expression is K factorial minus 1. And since Ui divides Uj, whenever I is less equals to J, you have this, UK is going to divide R plus K. And from that, we can show that, by the way, R and K are both positive integers. So R plus K is really greater than or equals to K factorial minus 1, which means that K is less equals to CR. So this is how one can prove that. And finally, another thing which was used is this one. This is formulated and proved by Professor Borisov. And he has a paper in arXiv, which he uploaded very recently, I think at the beginning of February, where also he uses something similar. I think it also appears with the proof in his paper. So this is what I was saying, that this is really a problem about the integers. There's a lot of technicalities here. Well, not a lot, but some. But here's the idea that suppose I have this sequence of integers and I'm using this interpolation polynomial to calculate the appropriate polynomial which generates this sequence of integers. Then if via interpolation, you are getting a polynomial which is not over Z, then there doesn't exist a polynomial over Z that generates this sequence. So interpolation is the answer, really. If you do not get a polynomial over Z using interpolation, then you're not going to get it in any other method. And that's precisely what this lemma says. And the proof is also very straightforward. So if we start with the sequence R0 up to Rn, which are all integers, And then we have some px, which we can assume px is the interpolation polynomial because we are assuming n-1, a degree at most n-1. And pri is equals to ri plus 1, where I lies between 0 and n-1. If there is some polynomial q over z such that they agree on these ri's, they meaning q and p agrees on ri's, then p must also be over z. The interpolation polynomial must also be over z. And well, the idea is simple. You can just write out some. Yeah, so qx is going to be like this, using the condition that's given here, because pxi agrees with pri agrees with the qri. So you will have something like this for some polynomial fx. And well, you can allow 0, I guess. And here's the thing, fx must be in zx. Otherwise, what's going to happen is this. This is degree n-1 at the most, and this is degree n. So if you get some coefficient here, which is lying over q, then this part right here it cannot offset that particular thing. It cannot make it go to z, using whatever extra is necessary in order to push it towards z. So the argument is basically that. So I would like to end the talk with 2 questions. First one is that this lemma that we considered, where is it? This one, for lemma 4.1. So we have said that k is less equals to CR. We have not said that k is strictly less than CR. So my question is, can this bound be improved? Well, in general, no. It cannot be improved in general. Why? Well, you can consider this polynomial. ux equals that, where r is k factorial minus k minus 1 for some particular k. I said k is greater than or equal to 3 just to make sure that r is positive, no other reason. And now we can check very easily that that this is a polynomial which is nilpotent at r of index k plus 1 and degree k. And also that u of r plus k plus 1 sec. I think there's a typo here. Yeah, I think there's no, there's not a typo, but I forgot to write it. So r plus k plus 1, it is not equals to, u of r plus k is not equals to r plus k plus 1. So that means it satisfies the sequence of equalities and also one inequality, or rather not inequality, it's inequation, I guess. And there is an r for which this happens. So in general, this cannot be improved. But my question is, if r is not of this form, can we say something about the maximum k? Well, why am I thinking of this problem? The reason is this. While I was computing this case by case things, for r equals 2, whatever the k value was, whatever the maximum k value was, I found some polynomials there. But as r was increasing, the last case where k was taking the maximum value, where k was taking CR value, in that case, I'm not getting any new polynomials out of it. They're always going to get, we are always going to end up with some false statement or some absurdities, so that we have to ignore those things or reject those things, sorry. So basically, that is a good question that one can think about, because I think that there might not be a universal bound, but we can improve the bound for whenever r is not of this form. This is what I think. And the question 2 is the one that I stated before, that if R is large enough, then is it true that there is nothing between R over 2 and R minus 1 index? It is certainly true for R equals 4. It is certainly true for R equals 5. Not sure if that goes on forever. Yeah, that's all I had to say.
Oh, thank you very much.
Thank you.
Thank you. That's
Are there any questions for our speaker? I have a couple of little questions. So just to make sure I understand the whole process, you have some number R that you're starting with, and you
Mhm.
have a polynomial U, and you look at the trajectory of R as under U. So you take R, U of R, U of U of R, and so on.
Yeah.
And
Yeah.
your polynomial is nilpotent if at some point you hit 0.
Yes,
Right.
but not at the starting.
No, no,
Yes.
yes. So where did this kind of question arise? Where does this come from?
The problem was stated not exactly in this form, but it was stated in a different context. This was a paper by Professor Borisov. So in there, he was looking at polynomial maps over Z and iterations of polynomials such that you have 0 modulo every prime. So and then we thought about understanding or trying to understand this in terms of just algebra or rings of integers, really. So first case was, of course, the trivial case Z. So we started working with these polynomial iterations, and there's modulo every prime. We are supposed to have 0, but there was always a question that what if we actually have 0?
Mm-hmm.
So it started like that. And then I talked to a lot of experts in this area, including Professor Tucker, and he said that not a lot of work has been done in this exactly looking at the 0 number. A lot of work has been done on polynomial iterations and polynomial sequences. There was this person, I think he was from Britain, R.W.K. O'Donnell. He has a lot of paper in this area. And in all of those, he basically talks about how badly you can fail with these primes. And most of the papers are like that. But classifications, I could not find anything like that. And the 0 was certainly interesting. So the first paper was about this understanding polynomial iterations, modulo primes. And the next step was would be, in this one, is just when you actually see the 0. And then what I'm working on right now is to generalize all of these things into rings of integers, arbitrary rings of integers. I have some results about local nilpotent polynomials, but not nilpotent ones, over all the imaginary quadratic fields, because the methods that we are using is to somehow make use of the fact that the number of units are extremely small. Well, if you ignore the rings of Eisenstein ring and a Gaussian ring, then everything else is just plus or minus 1 in the quadratic number fields. So a lot of things were in our control if using that particular method. And so I did Zi and this Zw, or Z omega rather, separately. It turns out that x plus 1 is still the only one polynomial which is locally nilpotent but not nilpotent if you start at 1. And using this thing that I mentioned, that R and minus R, if we have a one-to-one correspondence, this actually works. So why was this correspondence drawn? Because it was relating to the units, basically. So if you have more units, then you can still do this. It's just then R is going to be taken to gamma of R, where gamma is a unit, and vice versa. So everything, the definitions make sense, the ideas make sense, and of course, when I say primes for number rings, I actually mean prime ideals or non-zero prime ideals, to be more precise. So things make sense, but there were some places where divisibility had been used extensively, and there were some places where ordering were used. So these are some of the problems that I'm facing, which I don't know how to recover from.
Right.
I believe that something is going on with the degrees of inertia of the residue fields, and if I study this well, then things can be understood in a different way. But again, these are some of the examples. This is the impression that I have by working out a few examples. This is not in any way a proof.
Mhm. So, and one other quick question. Again, with the original, over the integers and the rationals, when you have, you said, if I understand it, if you have an infinitely nilpotent sequence in polynomial, you could have u of 0 equals 0, or u of 0 equals something, and then u of that something equals 0. So from that point on, your sequence is periodic with period 2. But
Yeah,
why is it not possible to have something which is periodic with period 3?
because of this theorem that I mentioned. So if you get to 0 at certain point, and you want to see 0 again, then it has to be either the next one or the one after that. There is no other possibility.
Well, no, I understand that's a theorem. I was asking why that's a theorem. Not like technically why, but why should you not be able to have a point of period 3 or 4 or higher? Is there like a simple way to explain that?
I think the idea would be that there's always going to be a prime for which you will get stuck. So I guess there is, it is not an answer to your question, but the main reason for this lemma was to understand where this sequence, like it goes up by 1, this stops, was that if u of r plus k is not equals to r plus k plus 1 or r plus k minus 1, then we can always reduce these polynomials with the ones that we know. So this we are calling reduction of polynomials formula. So if you have something u of x and you have a starting point, and let q be any divisor of the GCD of r and u of r, and then you define v of x to be a polynomial, which is 1 over q times u of qx, q being a divisor of this GCD, we can ensure that vx is indeed a polynomial over the integers. And by induction, it follows that q times v to the n, n iteration of v at r over q is equals to n iteration of u at r. So we can, unless q is equals to 1, we can always reduce these things to the smaller numbers.
So does all this apply equally well to points of any period? So if you're looking at the trajectory of a number under some polynomial, is there an upper bound to the size of a period?
Yes, that's right. And that upper bound is r, which was
the starting
r
point?
is, yes, that's right. I mean, of course, if r is greater than or equals to 3, then yes, r. If r is less equals to 3, then less equals 3 and greater equals to 0, then the maximum would be r plus 2.
Mm-hmm. So you can have points of period 3, but not going,
Yes.
not 0, coming back to 0.
Yes, which is right here. Right here. 3 goes to 4, 4 goes to 5, 5 goes to 0, or 3 goes to 2, 2 goes to 4, 4 goes to 0, using these polynomials. You can check that.
Mm-hmm. Well, but that's not a period, is it? I mean, it's not
So when you say, when you say period, you mean the distance, right? From where it's starting and when you're hitting 0. Is
No,
that
no,
what you
no,
mean?
no, no, no. I mean, a periodic sequence. So the sequence repeats 795, 795, 795.
Oh, I see.
Is period
see.
3.
Okay, I see. No, it doesn't happen. I mean, if it's like, because if you have something like that, then we can always select a prime for which a modulo that prime, the orbit is going to look exactly like that. Say for 795, we can pick 11, for example, as the prime, and then we will never see 0 modulo that prime. Or if you claim that, okay, fine, we have seen 11 before 795, then I can always look at the ones that we have seen before, and then add this 795 thing, and then take a prime which is larger than all of these guys, and modulo that prime. You are going to get stuck. You are never going to get 0. So in particular, this polynomial is not going to be locally nilpotent. And since this is not locally nilpotent, it cannot be nilpotent.
Right. Okay. Thank you. Any other questions for Sayak? Again, thank you for a very, very interesting talk.
Thank you.
Also,
Thank you for
give my
Thank you
regards
very
to
much.
Borisov, who I haven't seen for many, 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 many years. Next week, our speaker is Senior Shidvasar, who is here checking out how things work, and who will talk about ULAV sequences, which are very interesting. Any questions or comments before we quit for the afternoon and everyone can leave except David Ross, because I have a question for him? Senya, you'll
Yes.
be back in Maine?
Yes.
Yes. Is it cold up there?
I mean, yes.
I mean, is it colder than here?
It's for the most part, it's been a fairly warm winter, I'd say, but sure, it's Maine. It's, by Maine standards, it's
Right.
warm.
Okay.
I think you're still recording.
Oh, thank you. Let me stop that.